Hello everyone, I am Dr. Fawzul Atik. I am giving some series of lecture for the course Discrete Mathematics. So I'm sorry I got a little cold, so please bear with that. Okay, in the previous lecture, we discussed about the Pigeonhole Principle, right? And in today's discussion, we'll start with Generalized Pigeonhole Principle. What is that? So suppose you have set of 21 decimal digits, right? So you have 21 decimal digits. What are these 21 numbers? Decimal digits means 0, 1, 2, like that up to 9. So you have 21 such digits available, right? Now, what we can give guarantee that there must be at least 3 that are same if you have 21 like this kind of digit. Why? So how many total digits you have here? There are 10 number of digits, correct? And you have 21 digits available. So 10 total number of digits are there. Digits are possible, different digits. So there are 10 possible positions, basically. 10 positions are there. Now, among these 21, even if they are very equally distributed, so you may have like 2, 0, 2, 1, like 2, 2, 2, 3, like that, 2, 9. All of them are 2, 2, 2, 2 are possible. Then in this way also, how many you can cover? You can cover 20, right? Because each of them are at 2 are there. But you have 21 digits available. You still have one more remaining. So that one digit has to be there, will be one of them, has to be there in one of the box. So at least one of the box will have maybe 3 digits, correct? So if I have 21 total number of decimal digit, then at least 3 will be there who are the same digit. Why? Because if they are equally distributed, all of them can be the same digit also. It is possible. But what you can give guarantee that at least 3 will be there who are the same, right? So basically, what you are getting here, it is 21. It is 21 divided by 10. And if you take the ceiling of it, you are actually getting 3, this number 3. Let me tell you another situation. Suppose you have maybe 8, some pigeons are there. Okay, you have 8 pigeons and you have 3 holes. You have 8 pigeons and you have 3 holes. So these 8 pigeons you want to distribute among these 3 holes. It is possible that all 8 can be in the same hole. Possible. Or you want maybe in one hole 3, another hole 3, another hole 2. That is also possible. But what you can give guarantee, like maybe they want to make it very distributedly so that one hole should not get a more occupancy. So they can first pigeon come here, second is coming here, third came here. Then again fourth one come here, fifth one came here, sixth one came here. Then the seventh one will be here and eighth one will be here. So what you have seen, at least one box will be there that will contain 3 pigeon. Correct? So this is the generalized pigeonhole principle. So 8 by, if I have 3, because 8 pigeons are there, 3 are there. So what is this number? It is 2 point something, 2 point something. Ceiling of it is basically 3. So at least one box will be there which can contain at least 3 number of pigeons. This is the pigeonhole principle. I hope this is clear. We'll do a lot of example so that it will be more clear to you. Now, this one we have already discussed. Now, what is the generalized pigeonhole principle? If n objects are placed into k boxes, then there is at least one box containing at least n by k number of objects. Yes, that is what we have seen. So initially we had 21 objects, that means 21 digits we had. And we had 10 possible positions because maximum we have 10 different digits. And then we have given guarantee that 3 will be the same. So 21 divided by 10, ceiling of it. So 3 will be of same type. Correct? So this is called the generalized pigeonhole principle. Now, if your n is equal to k plus 1, then what is the question? If k plus objects are placed into k boxes, then what will happen? According to this theorem, it will be k plus 1 divided by k, which will be 1 point some value, 1 point some value. And if you take sling function of it, it will be 2. So it is coming like a pigeonhole principle. If your k plus object are placed into k boxes, then there will be at least one box which will contain two or more number of edges. So this is coming from the generalized principle only. That is why the name of this rule is generalized pigeonhole principle. I hope this is clear. Now let us understand through some example. Look at that. Among 100 people, there are at least 100 by 12 is equal to 9. 100 by 12 ceiling of it is equal to 9 who are born in the same month. Yes. So how many different month you have? 12 different month you have, right? And you have 100 people. You want to check their birth month. So how will do? So even if they are distributed very well, but by generalized pigeonhole principle, among them, there will be 9 people who will born in the same month. That you can keep guarantee. I hope this is clear. Okay, the next one. What is the minimum number of students required in a discrete mathematics class to be sure that at least 6 will receive the same grade? If there are 5 possible grades are available, A, B, C, D, E, F. So suppose your discrete math course have maximum 5 grades, A, B, C, D, and F. Now the question is, what is the minimum number of students required such that you can give guarantee that at least 6 will receive the same grade? Now it is possible that all may get A, all may get A and B, but you cannot give guarantee of that, right? But what you can give guarantee that what is the minimum 6 number of is the guaranteed that many will receive the same grade, whatever may be the grade. What will assume? Let n is the minimum number of students required. Let n equal to the minimum number of students required. Then what will happen? So at least 6 will receive the same grade. And how many possible grades are there? 1, 2, 3, 4, 5. 5 possible grades are there. That means what? N students receive the maximum 5 grades. So by generalized pigeonhole principle, we'll have n by 5 should be the, like it should be at least 6. Now what is the minimum number n, capital F, such that n by 5 equal to 6? N by 5 ceiling of that it is equal to 6. Yes, so you may think that okay, n equal to 30. So it is 6. But is that n equal to 30? If I put n equal to 30, then in 30 by 5 ceiling of that it is 6. Fine. But is 30 is the minimum one? What about 29? 29 by 5 is equal to 5 point something. 29 divided by 5 is equal to 5 point something. And ceiling of that it is again gives you 6. So 5 is not, 29 is not the minimum then. Like 30 is not minimum, 29. Okay, let us see whether less than 29 is also possible or not. Check with 28. Yes, 28 is also giving that 6. Check with 27, giving it 6. 26, still it gives 6. If n equal to 25, then n by 5 is equal to what? No, in this case, if n equal to 25, then ceiling of n by 5 gives you 5. No, then n should not be 25. What is the minimum then? We have checked that n equal to 26 was also giving. So n equal to 26 is the minimum number required. Right? And how you can make it? That less than this 6 we have, right? So what you will do, it is you can make like a formula type of thing, because in 5 a 5 into 6 was giving you 30. 5 into 5 gives you 25. So one more than that is required. So the minimum number n is actually equal to 5 into that 5, but not exactly that. One more than that is required. So then this is plus 1 should be the answer. So then the minimum number of required student is 26 here. I hope it is clear. Okay. Yes, this is how we have discussed. So n equal to 5 into 5 plus 1 equal to 26 now. We'll discuss one more problem here. Let's see. Look at this problem. How many cards must be selected from a standard deck of 52 cards to guarantee that at least 3 cards of the same suits are chosen? So in a standard deck of 52 cards, how many minimum number of cards you can choose so that you can say that at least 3 cards are of same suits? See, you may possible that even the first 3 choice you may get the same suits of card, but is it guaranteed? No, no. So first you think how many different suites of cards are available total. If you know the card, if you have idea about card, how many different suites of cards are available? There are 4 different suites of cards are available, right? 4 different suites of cards are available. What are they? That is diamond, club, right? Heart and spade. Now, suppose you pick the first card. You may get one card. The second card, you may get different one. Third one, you may get different. Fourth one, you may get different one. Then fifth one onwards, one will be repeated. Sixth one onwards. Then again, sixth one can be the same. So you assume that, let's assume that there are like n number of cards are minimum required cards are there. So minimum of n number of cards are required. So assume that let n equal to the minimum cards are required. Minimum number of cards. Then what is your answer? Like let us form the problem. It is n cards are there and distributed among 4 cards, right? And then you should get at least 3 among them. So your answer is, what is this n such that you will get this n by 4 ceiling of that is equal to 3. Now you tell me what is your answer. If you take n equal to 12, 4 3s are 12. Okay, it will be possible. But is 12 is the minimum number? No. Then go back. 11. 11 is also giving you 11 by 4. Ceiling of that, it is ceiling of 2 point something. But it is giving you 3. 11 is also giving 10. 10 will also give. 9 also gives. What about 8? 8 by 4, it is 2. No, it is not giving. So 8 is not the minimum. So next is 9 is the minimum. But how you can think? You can think that n minimum number n is such that it is 4 into 3 was 12, but it is not minimum. The 4 into 2 is 8. It is not, it is giving 8, but one more than that will give you the answer. So it is 4 into 2 plus 1. Right? So minimum number of card required, it is 9. I hope this is clear. Okay. So this is how the generalized pigeonhole principle works. Clear? Okay. Yeah, this is one we have discussed, and then the answer is 9 for this problem. Now we'll discuss the permutation. Now, many of you know a little bit about a permutation. What is that? It is the number of ordered arrangement. It's an arrangement and it's an order matters. Right? Let us understand permutation through some example. Look at this question. How many ways can we select the 3 students from a group of 5 students to stand in a line for a picture? So you actually want to make a picture like this, stand in a line, and there are three students you want to take a picture. But how many students you have? Total number of students are 5. And now here, this 3 student, whenever you will take a picture of it, maybe the students are A, B, C, D, and E. These 5 students are there. Now, how you will take the picture? So, suppose how you can choose. Like in the first position, maybe the student B is there. Second position, maybe the student D is there. First position, student A is there. This is possible. So, this is one arrangement. In another way, the first position may be D, and here it is B, and it is 1. But these two are different, right? Because here B is in the beginning, D is the second one, A is the third one, whereas this one, D is in the beginning, B is in the middle, and A is in the. So they are different, correct? So this is how you have to arrange it. So how many different ways you can do that? Now, we all know the product rule of counting, right? In the previous lecture, we have learned that. So you divide the task into 3 parts. First part is for the first position, first count how many possibilities you have. For the second position, how many, and for the third position, how many. Now, whenever you are choosing for the first position, how many students you have, it is available. You have 5 students are available, right? Any student can be there in the first position. So first position can be done in, fill up in 5 ways. Then once the first position is done, for the second position, how many students are available? Because one student is already occupied in the first position. So for the second position, you will have 4 number of students available. Then you think for the third position, how many students are available? So already you have filled up with first position and second position. So 2 students are already done. So for third position, you have 3 students available. So first position you can fill up in 5 ways, second position you can fill up in 4 ways, third position you can fill up in 3 ways. So by product rule, how many ways you can do? 5 into 4 into 3. Is that clear? So this many ways you can select 3 students from a group of 5 students to stand in a picture. So that means this many permutation you can do. These are all ordered arrangement. Right? Okay. There is another part of it. How many ways can we arrange all 5 students in a line to form the picture? So for the second part, you are asking, you have 5 students and you have 5 positions available. You have 5 positions are available. How many ways you can do? Do it in the same way. First position you fill up with 5 ways, second position 4 ways, then 3, then 2, and then 1. So by product rule, how many? 5 into 4 into 3 into 2 into 1. It is what? It is basically 5 factorial, right? So how many ways you can arrange? 5 factorial ways. Clear? This is the concept of permutation. So permutation, to get that ordered arrangement, we are taking the help of product rule. Correct? Now come to this problem that we have already discussed. So the first problem, we need 5 into 4 into 3. So 60 ways are there. And for the second problem, it is 5 factorial, which is 120 ways are there. Now the definition of permutation. A permutation of a set of distinct objects is an ordered arrangement of these objects. An ordered arrangement is what? Just now we have discussed that you will have some arrangement and where orders matter. That first A, B, and C and B, A, C are different. That kind of orders matter here. Then an ordered arrangement of R element of a set is called a R permutation. An ordered arrangement of R element of a set is called a R permutation. And then the number of R permutation of a set with n element is denoted by PNR and can be found using the product rule. Just now we have done it for this example. So like A, B, C, it is one of the permutation, 3 permutation. Or C, A, B, it is a 3 permutation. Right? This is an example of a 3 permutation. This is an example of a 3 permutation. And how do you denote the number of, how many number of such permutations are available? Suppose I have 5 objects. how many such kind of permutations are available, that you denote it by P5R. So among the 5 objects, you are finding how many 3 objects are arrangements are possible. That you denote it by P5R. That means the number of R permutation of a set with n elements is denoted by PNR. And how we have calculated? We have done it using product rule, right? For this one, P53, in that case, what we have done? So for the first position, we have 5, second position 4, third position we had 3. Like what we have done, right? In some other cases, suppose I have 10 objects are available and I want to calculate the 4 permutation among them. How many ways you can do? So for the first position, you have 10, second position 9, third position 8, fourth position you have 7. So this many ways you can do. So by the same way, what will be our PNR? What will be our PNR? PNR is R number of permutation you have to find out how many are there from n elements. So for the first position, so there are R positions are available. So first position it is n, next is n minus 1, then n minus 2. How many are done? 3 are done. In this way, how many you have to do? You have to get R number of. So it will become, so see for the first position it is n minus 0. For the first position it is n minus 0. Second position it is n minus 1. Third position it is n minus 2. Right? Similarly, for the R position, what will happen? It is n minus R minus 1. So this many ways you can do. So this is the formula for R permutation. Then how many ways you can do? N into n minus 1 into n minus 2 by product rule, n into n minus 1 n minus 2 up to n minus R minus 1. Clear? So this is how you can able to find the number of R permutation of a set with n elements. Yes, that is what we discussed. So if n is a positive integer and R is an integer with 1 less or equal to less or equal to n, then there are P and R equal to n minus 1, n minus 2 up to n minus of R minus 1. That is basically if I remove the bracket, n minus R plus 1, R permutation will be there. Clear? How we got this formula? Using the product rule. Correct. Now, this formula PNR, I can write it in this way that n into n minus 1 was already there, n minus 2, dot, 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 n minus of r minus 1. But this n minus of r minus 1, how we are writing? We are removing this bracket. Then what will happen? If you are removing this bracket, what will happen? It will become n minus r plus 1. Correct? So this is our this formula. But this one I can write it as n into n minus 1 up to n minus r plus 1. And then I am multiplying few more extra term in the numerator. What is that? N minus r. Then n minus r more minus 1. Up to that, I will go up to 3 into 2 into 1. Correct? Then I have added these terms are new. I have added these terms are new in the denominator. So I have to divide them. N minus r plus 1 up to 3 into 2 into 1. But what is this value? You have started from 1, 2, 3, 4, all this way up to n. So is it not the value of n factorial? What is the denominator value? 1, 2, 3, 4 up to n minus r. Is it not the value of n minus r factorial? So therefore, the formula for PNR is equal to n factorial divided by n minus r factorial. So this formula you probably know from your childhood level. Correct? Okay. So then if n and r are integer, then p and r equal to n factorial by n minus r factorial. So this is how the formula for permutation comes into the picture. I hope this is clear. Now we'll do few examples. Okay. So S is equal to 1 to 3. Is a set. The order arrangement like 3, 1, 2. This is one permutation. It is basically a 3 permutation. Then 2, 1, 3. This is another 3 permutation. right? The how many ways you can do? You can make all these things. It is 3 factorial because 3 elements you are multiplying 3 permutation from a 3 element set. It will be 3 factorial by 3 minus 3 factorial, which is basically 3 factorial. Again, how many 2 factorials? So 3 comma 2, this is a 2 permutation. Or 1 comma 2, this is another 2 permutation. How many 2 permutations are possible from the set of 3 elements? It is P 3 2. So basically 3 factorial divided by 1 factorial. So in this case it is again uh, 3 factorial divided by 3 minus 2, so 1 factorial. So it is again 3 factorial. Clear? Okay. Now, look at this problem. This is very interesting. How many ways are there to select a first prize winner, a second prize winner, and a third prize winner from 100 different people who have entered in a contest? See, you have 3 positions, right? First position, second position, and third position. How many ways you can do? You have 100 participants. So while choosing the first participant, among the 100, anyone can be there to get the first position, first prize. So 100 choice I have. Now once I have the first position, I'll choose for the second position. So I'll have how many ways are there? Because one student already got first position, so I have 99 choices available. So once I have first and second position done, how many students are available to get the third prize? 98 students are available. So how many total number of ways this can be done? It is 100 into 99 into 98. This is the answer. Or basically this is an ordered arrangement. Correct? So this is basically you have to find the 3 permutation from a set of 100 element. So permutation formula is P100, 3. That is actually basically this answer. It is 100 divided by 97. 100 factorial divided by 97 factorial. This is equal to this answer. Clear? So this is just a direct application of permutation. Therefore, it is a 3 permutation from a set of 100 element, and the answer is P100, 3. So this is the final answer. Clear? Okay. Next problem. Look at this. Suppose that there are 8 runners in a race. The winner receives a gold medal. The second place receives a silver medal. Third place finisher finishes the bronze medal. The question is how many different ways are there to award this medal? If all possible outcomes of the race can occur and there are no ties. So see, you have 8 runners available. And how many different prizes are there? 3 different: gold, silver, and medal. Right? Gold, silver, and bronze. So 3 different prizes as possible. So how many ways you can do? Basically, it is again an ordered arrangement. Right? So it is P 8, 3. That should be the answer. Correct? Or you can think in that product tool. Product tool is the base of permutation. So the first position you can fill up with first gold medal you can give it to all 8, any one of the 8. So 8 possibilities. Then the second one is 8, 7 position possibility, and the third one is 6. So 8 into 7 into 6. So basically it is same as P83. Clear? So this is the final answer, P83. 336 possible ways to award the medals. Okay, I have one more problem. Look at this. Okay, what about this one? Suppose that a salesman has to visit 8 different cities. She must begin her trip in a specified city, but she can visit the other 7 cities in any order she wishes. How many possible orders can the salesman use when visiting the cities? See, there are 8 different cities available, right? 1, 2, 3, 4, 5, 6, 7, and 8. And how many ways she can start with? She can go from any way. So it is basically how many possible orders she can follow among the 6 eights. That means you have to basically find the permutation. But there is a trick. Here that she must start with her trip in a specified city. So the first city she has to go with, start with one particular city. So this is a fix. So for this one, you have only one choices. Then for the second one onwards, she can have any. So you have total number of 8 choices of cities. First city, it's a specified one. She has only one choice. Second one onwards, she can go anywhere. So second one, how many choices she have? 7 choices she have. Once the first and second are done, third one, how many choices? 6. Then it is 5, 4, 3, 2, and 1. By product rule, how many ways she can do? It is 7 into 6 into 5 into 4 into 3 into 2 into 1 into 1. It is 1 into 7 factorial. Basically, it is 7 factorial ways she can visit the cities. Clear? So this value is actually 5040. So she can visit this many ways. Right? I hope you understand. Okay, the last problem. How many permutations of the letter A, B, C, D, E, F, G, H contain the string ABC? See, you could have made the permutation. If I ask only that how many permutations of the letters A, B, C, D, E, F, G, H have, what you will answer? So A, B, C, D, E, F, G, H, A, B, C, D, E, F, G, and H. How many are there? There are 8 numbers are there, right? There are 8 such numbers. If I ask you how many permutations are there, you know the permutation formula, 8 factorial is the answer. But here the question is, how many permutation contain the string, the block ABC? So that means where, suppose one of the example maybe I'm giving D, E, A, B, C, then H, G, F. This is a permutation, right? Where these three are together. Now the question asks how many such kind of permutations are available, right? For the letters A, B, C, D, E, F, G, H. How you can do that? See, basically that means where A, B, and C are together in this form are there. That is how you have to find out. What you can do, just make that A, B, C is a single element. It's a block. And then others next onwards, they are the single alphabet. D, E, F, G, and H. Then find the total number of permutations. That will gives you the where the block A, B, C are together. Correct? Now, how many numbers are there? 1, 2, 3, 4, 5, 6. So that means 6 element you have, and you have to permute all of them. You have to permute all of them. How many ways you can permute? We know the permutation formula. 6 elements are there. All 6 will be, you need that all 6 permutation. So it is basically P6, P66, which is basically 6 factorial. So there are 6 factorial number strings, number of permutations are there, which contain the string A, B, and C. What is the value of 6 factorial? It is 720. Clear? I hope this is clear. So this is the final answer of it. So you can make a block, and then there are 6 factorial permutations are there, where the string ABC will be appearing. All this content I have taken from this book only. So let me end the class. If you like the video, you press like the button. And if these videos are helpful, you may share with your friends. You may share with any other people who need it. You may write your comment, give your feedback. And please subscribe this channel. I hope this channels contain another playlist, which is the probability and statistics. That is also helpful for you. So I'll also get some motivation. Thank you very much. We'll come up with a new video in the next lecture. Thank you. Bye-bye.